So today I'll be talking about the Rutherford and Bohr model of the atom. So back in the 1900s, in the year 1900, most people believed that the atom was made of positive and negative charges made up into one ball. They thought that these charges interact with each other and that they're more how we see the metal cations right now, where there's more of a sea of positive and negative charges in this little ball, much like this plum pudding. That all changed when a scientist by the name of Ernest Rutherford designed this experiment to test radioactivity. So what Rutherford did was he took uranium and put it in this lead box. And in that box, he put a little piece of uranium and let it decay. And as it decays, he knew that they produce what's called an alpha particle. He didn't know it was an alpha particle at the time. He just assumed that they were these relatively massive, positively charged particles. And so he basically aimed the box so when it fired out these alpha particles, they would be shot in one direction. And then he placed this gold foil in front of it, and then placed a screen or a film all the way around it so that he could be able to measure where the particles went. So Rutherford assumed that because of the relative size of the particle and the thickness of the gold foil, just for comparison, the gold foil that he got to 0.4 of a micrometer. And just for comparison, a piece of hair is 25 micrometers across. So very, very, very thin piece of metal foil. And so he assumed that the particle would just go straight through. And he assumed this because the plum pudding model, according to the plum pudding model, the dispersal of the charges wouldn't have been enough to deflect any of the charges. He guessed that there may have been some deflection, but very, very, very little. So when he performed the experiment, it was much to what he expected, except he got these little deviances. And we're talking just little bits when he went through. More than the gradient that he was expecting. What really surprised him was that every once in a while, every long while, he would get one way over here, or way over here, or way over here, like back against towards the screen. And that ended up being one about every 20,000 particles that they measured would come back. And he was just perplexed by this because he always described it as a cannonball being bounced back by a piece of tissue paper. And so what he discovered by this is that the plum pudding model that everyone had assumed for so long could not be true. So he realized that there had to be something different. And so he proposed the new model of the atom had to be something in the middle that was both tiny, because most of the particles didn't. He assumed that they were tiny because most of the particles didn't interact with it. We're talking one out of every 220,000 interacted with it. So it had to be very small, and the atoms had to be mostly made up of empty space for the majority of the atoms to just pass through unaffected. He had assumed that it was also massive. And the thing is, a lot of people think these are contrary points, but when you think about it in terms of a momentum, these particles had to be massive enough to bounce back the alpha particle. That means they had to be massive in size enough to repel and not be just blown out of the way when they interacted with the alpha particle. He also said that had to be positively charged. Positively charged. He assumed this because by the fact that these particles were repelled. If they were negatively charged, they would have been attracted, and they wouldn't have repelled in the way that they did. So he proposed that the atom now, the model that he proposed, is the one that we kind of assume when we look at the atom. A positively charged center with these little electrons. So he knew that there was negative aspects of the atom, but he knew that the center had to be positive. His model didn't show anything about the negative aspects of the atom, and so he proposed that the center was positive, and then just proposed an idea that these negative electrons just circled in orbits. He proposed this because in his mind of how the world worked, he thought about the planets and the orbits. He thought it was logical for him to assume that the electrons just orbited around the atom. And so he proposed this model that stood for a couple years until his actual pupil, someone under him, Niels Bohr, came up with a different model of the atom, or expounded upon that model of the atom. So Niels Bohr took this model of the atom with this positively charged center, and he expounded on the idea of what these negative molecules, these negative particles, these electrons would be doing, because he understood that a charged particle, in this case the electron, could not be maintained in orbit. He understood that the electron, if it were to remain in orbit, would be losing power as it went in orbit. Therefore, it would be losing its radius and eventually fall into the nucleus. He understood that because molecules are not being destroyed at all times, this would destroy the molecule, and he understood that elements are for the most part stable, and this is not happening, that the electron could not just be being maintained in a static orbit. And so he proposed a new model from looking at light from elemental spectrums. He saw that when energy was put into a molecule, energy would be released from molecule corresponding to that level. So he saw that when he put in more energy, he would get energy over here in the blue range, and when he put in less energy, he would see these lower energy releases, blue being higher, red being lower. And he also saw that, for one thing, that these energy releases were quantized. When you say quantized, what I mean is that you can think whole numbers, right? So it's either 1 or it's 2 or it's 3. An example of something that's not quantized would be decimals, where it can be anywhere the integers between, or the values between 1 and 2 are infinite. That's an example of something that's not quantized. Quantized means it's either 1 or it's 2, and you can see it here. It's either here or it's here. It's not in between. There's no in between area. It's here or it's here. This in between area is not included in the light spectrum. So what he proposed is that there were orbitals, not orbits, meaning that there's energy levels that these electrons sit when receive energy, and that energy level, that orbital level, is exactly proportional to the amount of energy that is received. And you can think about this in terms of the game of the Flappy Birds, Flappy Birds, where think about it in terms of potential energy, where every time this bird goes up, it's receiving the amount of energy, and that for it to come down, it will release the energy, much like the potential energy models that we all know. What Bohr understood is that for a particle to go from here to here, it would have to receive an energy level proportional to that. It would have to, let's just use the purple example that it has, and so it would have to receive a purple level of energy. Let's say this is 100 joules. It will have to receive 100 joules to get to this level, and then it will sit up into this level, and then to come back down to here, it will release 100 joules. So it's the same idea of the conservation of energy. 100 joules in will bring it up to this level, or 100 joules will push a ball up a mountain. 100 joules will push this up the mountain, and then falling down the mountain, it will receive 100 joules of energy. At that, it will emit 100 joules of energy. So from this, we get this idea of these spectrums, that if I put in this amount of light, this amount of energy, I will get out the color that is proportional to that amount of energy. Now this model went on to, Bohr proposed this model, and through later experiments and later scientists, we have gotten what we now know to be the shell or orbital theories of chemistry and molecules. These ones were not done by Bohr, but this is where we get this s orbitals and the p orbitals and the d orbitals and these electron shells that we now know govern most of the laws of chemistry. And so these were the models and ideas proposed by both Bohr and Rutherford. You can see that they did not have all the answers themselves, but their contributions to the atom now constitute our modern understanding of the atom. And thank you.